Okay, so let's see. This is 6.3, number 46. Was one of the ones that was requested, highly requested. So doing this one, it actually refers us back to 6.2, number 63, which is finding the volume of a torus when you rotate this circle right here around the y-axis. The overall radius of that rotation is going to be a capital R. So let me go ahead and just plot a point right here. This point is at capital R, 0. And then the minor radius, the radius from here to here, is going to be little r. Again, that's what they gave us in that problem. And I'm not actually going to draw this out, but I'm just going to go ahead and do this volume of rotation. Now, in section 6.2, when we did this in class, and we did horizontal slices. We are no longer restricted to doing horizontal slices. We can now do vertical slices. So a slice like this, and I'm not even going to bother going down below the x-axis, because if I rotate that slice all the way around, I would get an object that looks sort of like, if I rotated it around, sort of like that. Okay. And it would be hollow on the inside, so it might look something like that. Okay, but I would get an object like that, and the volume above the x-axis would be the same as the volume below. So what I'm going to do is just find the volume of the solid above the x-axis, and it would look like the upper half of a bagel, and then double it up. That's all I need to do. So first of all, I'm going to note here that this is some delta x, and the volume of the ith slice is going to be, well, there's a distance going around this shell, so it's a circumference, 2 pi. I'm going to say 2 pi times the radius here, because all the r's, unfortunately, are being used, times the height of that slice, H-E-I-G-H-T, and then times the width of that slice. All right, the radius of that slice. So the radius of the rotation there is the distance from the center axis of rotation, this right here, all the way, sorry, I wanted to draw in there the rotation, all from the distance from the center of the axis all the way to that point right there. And that point is just an x value. It's whatever x value we happen to be at. So that point is x sub I, and the left point right here is x equals 0. So the radius of that slice is going to be x. So let me write that in here. This is going to be 2 pi times x sub I. The height of that slice that I have there, that I drew in blue and then highlighted here in red, the height of that is the y value at the moment, so y sub I. So I'll write that in here, y sub I. And the width is a delta x. It's actually a very nice, clean-looking volume formula. The only problem is we cannot integrate something that has x's and y's. So because it's a delta x, I want to go ahead and rewrite that y in terms of x. And luckily, the y value for this circle there is related via the equation of the circle. And the equation of the circle is x squared plus y squared is equal to r squared normally. However, it has been shifted, so it's x minus capital R squared plus the y value hasn't been shifted. And then the radius of that circle is a little r. Okay? And squared. I forgot about the little squared there. Now, if you recall, when we did this in class, the capital R came into play. Oh, actually, it is coming into play right now with that x minus capital R. So there we have it. It comes into play. All right. We're only, as I said, filling in and shading in this upper half of this circle. So I only am really concerned about the upper y values. So when I solve this for y, I will get plus or minus the square root of little r squared minus the quantity x minus capital R and quantity squared. However, because I'm only really worried about the positive y values, I will only worry myself with the positive square root. So this volume is going to be 2 pi x sub I times the positive square root of little r squared minus the quantity x sub I minus big R being squared, and finally delta x. And now I just want to find the volume, right? Now, if you think about the volume here of this rotated region, we're starting at an x value here, and we're ending at that x value right there. The first x value is going to be, well, capital R minus little r, right? You had to get all the way over to this capital R, and then you're subtracting off the radius. And then the other x value is going to be capital R plus little r. That should make sense. So when we compute the volume here, the true volume, we're going to integrate from x equals capital R minus little r to x equals capital R plus little r, and then insert that 2 pi x root quantity little r squared minus x minus capital R quantity squared, and then dx. And now we have to figure out how to integrate this. This looks to be somewhat challenging to integrate. It actually will not be too terrible. Oops, and I forgot to mention here, remember we are doing 2 of those, right? Because we have the upper half of the circle and then the bottom half of the circle. Now, really, there is sort of, I said it was going to be a simple integral, but actually there is sort of a trick here. Not too much of one, but still one that you might want to use. I'm going to go ahead and do a u substitution. So I'm going to say let u equal x minus capital R, and that'll imply that du will be dx. And it also will imply, because we have that lone and rogue x right there, that will also imply that x is equal to little u plus r, capital R. So let's go ahead and see what this u substitution, because it really is, it hinges upon this u sub. I mean, you could possibly do it other ways, but I'm just thinking that maybe this is the only way to go about it that's easy. I'm going to factor out that 2 pi. I get a 4 pi out front. And you integrate. Now remember, x was going from capital R minus r to capital R plus r. Well, if x is a capital R minus r, then u is equal to capital R minus a capital R, or in other words, a negative little r. And if x was a capital R plus r, u would be a big R, or a little r there. And again, x is now replaced with the u plus capital R, and we have the square root of little r squared minus little u squared du. And this is actually a little bit cleaner if you distribute through. So I had said that it's somewhat of a challenging integral here, but only because if you try to go one way with it, in other words, if you multiply out the stuff in the radical, or the radicand, if you multiply it out and try to do a u sub after the multiplication, you'll see that it won't work out. So then you should step back and try a different u sub. That's the only technique you have at that moment. So in this case, again, you might be stuck a little bit, but if I distribute, I'll get 4 pi times the integral from negative r to r of u root r squared minus u squared du, plus 4 pi times capital R integral from negative r to positive r of the square root of little r squared minus little u squared du. And that is actually a lot easier to work with. This you should recognize as the area underneath a curve, right? So that is sort of saying that if y is equal to the square root of little r squared minus a little u squared, actually maybe I should rewrite this in a format that you can actually see. So let me go down a little bit more. I'll say 4 pi negative r to r of u square root of r squared minus u squared du. And remember, I said this in class the other day, but it's probably worth repeating, is that once you're dealing with an integral and everything's in terms of a variable, like in this case, it's du, and there's my u, and this is u going from negative r to u going to positive r, you don't have to use that letter, little u. You could trade it out for x's if you want to. It doesn't really matter. So I'm going to say, well, we were going from x equals negative r to x equals positive r. And I'm just going to trade out the letter, the picture. That's all I'm doing. And that way, it makes the argument a little bit easier for you to see. So if I said that y was equal to the square root of a little r squared minus a little x squared, that would imply that you're dealing with a circle of radius little r. Whoops, well, that doesn't make sense, but of radius little r. And you're finding the area of that circle from one side to the other side. So really, you're looking at what's the area underneath this circle from negative r to r, and it's only the positive y values. So really all you're asking is, what is the area of half a circle of radius little r? So that part we can compute. The other part is a simple substitution. We already are using the letter u, so I'm going to say let v equal little r squared minus u squared, which means that dv is equal to a negative 2u du, or in other words, 2u du is equal to a negative dv. And so our integral becomes, well, I'm going to steal out from that first integral here the du, the u, and then a 2 from that coefficient. So when I do that, I end up with the following. A negative 2 pi, the negative comes from the fact that there's a negative dv involved now, times the integral. I'll take care of the limits a little bit later. The stuff with the radicand, r squared minus u squared, I'm going to trade out for a v, and it was the square root of v. And we have that du being traded out for a dv with a negative that we wrote out front. If you're going from a negative r squared to a positive r squared, well, this is kind of interesting, right? If u is a negative r squared, you get 0. If u is a positive r squared, you get, well, a 0. So what is happening here? Well, this actually harkens back to something we said in class the other day, which is that if, or I might have said this in class the other day, it just depends. But anyway, if you're integrating over a symmetric interval, in this case, we're integrating from a negative r to a positive r, and if your integrand, in this case, our integrand is this business right here. If your integrand is odd, and in this case it is, our integrand is odd, then that integral should be 0. So that's kind of neat. That integral actually disappears. It's just 0. And like I said a moment ago, this integral, the one that's from negative r to r of that, is just the area underneath that curve right there, half the area of a circle. So times 1/2 pi r squared. So in the end, you get, remember, this is 0 plus 2 pi squared r little r squared, or in other words, just 2 pi squared little r squared capital R. And that should agree with what we did in class and when we were in section 6.2.